So welcome to today's lecture about how to train a neural network. And I want to show you first what we have talked in the last lectures about. And we were talking about how neural networks are structured. So you have an input layer, you have hidden layers, and you have an output layer. And the input layer is nothing else than your observations. The hidden layers is where you learn a new representation of your data, which is very suitable for the output you want to have and to solve the specific task you have. So the output is exactly what you want to have, either labels or some continuous output or something else. And we were talking already a little bit about the training setup. That means neural networks are not that easy to optimize. And there are several things you need to think about, which ensures a better and more efficient, faster training, and to reach a solution you want to have. So we will talk today about data preprocessing, about some architectures. That means specific architectures and the design of layers and the number of neurons you need for specific architectures, the activation functions and how they influence the whole optimization process, the data preprocessing, which is important for neural network training, but which is totally depending on the community and the research area you're working in. The initialization strategy, that means how you can initialize the weights in the neural network, because you have a lot of parameters and somewhere you need to start. And we were talking about the loss landscape, and depending on the initialization of your parameter set, you start somewhere in this loss landscape. And of course you want to start somewhere which is good and close to some optimum. And also you need to think about the loss function and evaluation strategies. So let's start with the activation functions. The most commonly used activation function, or one of the most commonly used activation functions, are sigmoid, tanh, and rectified linear unit, short ReLU. Sigmoid and tanh function are squashing function. It means your input is squashed into a specific area. For the sigmoid function, it's between 0 and 1. For the tanh function, it's between -1 and 1. This can be really, really useful, but sometimes this can also cause problems. ReLU is a little bit different. It does not squash your input, but it restricts the input that in a way that it cuts off all the negative values. And as I already said, some of these activation functions, when you use them, they have really nice properties, but they can cause problems. Common problems are saturated gradients, vanishing, and exploding gradients. What does it mean exactly? When we talk about saturated gradient, it means that you have the same gradients, although you have a different input. That means at some point it doesn't matter which input you're feeding to your network, the gradients are just saturated to a specific value. When you have vanishing gradients, this happens especially when you have deep networks. It happens when you multiply small gradients. At some points they're close to 0 and nothing will happen anymore. You get some updates, but not for the weights in the deeper part of the network. The other extreme are exploding gradients. So it's when you have here, you do not have small values, but you have very large values. And when you multiply large values with large values, they get even bigger. At some point, the whole system just explodes. When you translate this to the loss landscape, it means that you're at some point, either you're stuck at some point, or you just jump around in this loss landscape, or you go very far away from an optimum you want to reach. So first, let's have a look at the activation function sigmoid. And the first thing you can see is that the input to this activation function is squashed between 0 and 1. And this is exactly the behavior you want to have when you have a classification task, and as output you want to have some kind of score or probability. So when you have an output of 1, you can immediately relate it to a highly probable output, and also when you have an output of 0, you know this is not an output an output which does not point you to the specific class. Another problem you can see is that of saturated gradients. Here, for example, when you have a look at the -10 and +10 area, and also values which are even larger or even smaller, it doesn't matter if you input +10 or +20. You will always get an output of 1, and the same is for the area of -10 or -20. It doesn't matter. You will always get an output of 0, and so that means that because the function is saturated, and when you have a look at the derivative and the reciting gradients, you will see that the gradients in this area are saturated. So, and normally what you want to have is, if your input changes, you also want the output to change and the gradients to change. Another problem with sigmoid is that it's not zero-centered. What does this mean? When you look at where the function is for when x is 0, it's at 0.5. That means this function never has values in the negative range. So it's slightly shifted. It's not centered around 0. And the result is that the output is always positive. It doesn't matter what you feed in, you will always get a positive output. And when you have a look at the gradients and the derivative, the gradients will always be positive as well. And so when you have a look at the whole backpropagation process, and the output or the very last layer will give you a positive or a negative value. This is the decision maker about what are the gradients, which sign the gradients have in the whole network. And this is not good, because this leads to the so-called zigzag behavior. So when you think of, you have a negative gradient in the very last layer, all the other gradients are multiplied, and they are positive, so the overall gradients are all positive. That means the gradients are shooting in one direction. Mostly it happens that they are going too far. And then in the next backpropagation step, you will realize that that was too far, so you need to go the other way. So you will have a negative value, and then it shoots back. So, and then you have this kind of zigzagging behavior, because you always go extremely in one direction, then you go extremely in the other direction. There's no in between, no middle. So that's why it's good when you have some weights which change in a positive way and some weights which change in a negative way, and not all weights changing in the same direction. The last thing also, you can see that there's an exponent, and the exponent is computationally expensive, more expensive than some other linear methods, for example. What is used more common nowadays is ReLU. Exactly because of the negative characteristics I mentioned on the last slide. What you can see here is ReLU just cuts off all the negative values, and in the positive region it does not saturate. It normally converges faster than sigmoid or tanh, and it's because there's no exponent in it, it's computationally efficient. So it's on the one side efficient, on the other side faster. So this is good, because when you train a network, you want to have a very fast and efficient solution. Again, you have the problem that it's not zero-centered, which leads to the problem that some neurons just die. What does it mean? When you have neurons where you have negative values, they do not fire, because they will result in 0, and also the gradient will be 0. So they just do nothing and do not contribute to in any way to a better solution or getting a better solution. This is a typical behavior, but it's accepted, because mostly it's not that bad that you have some neurons which just do not fire and which are 0 all the time. But you just need to be aware about this, that if you have at one point a neuron which does not fire again, that means when it's 0, it's very hard to get this neuron to and the gradient resulting from this neuron to get back into an area where you can make an update again. As a suggestion, what works mostly in practice is you first of all should prefer ReLU over sigmoid in tanh. What I said, sigmoid is a good choice for a very last layer when you do classification tasks, but in between it's mostly better to use ReLU. It has a better behavior and generally lead to a much faster convergence. There are some studies, and these studies, for example, say that it's about 6 times faster than sigmoid. But you need to be careful with the learning rates. This is exactly what I told you on the last slide. When you choose not so good learning rate, this will result that that some neurons just go into this negative area, and then you cannot do an update anymore. When you observe some bad behavior, or that your network is not converging in a way you want it to do, you can try some modification of ReLU. For example, there's ILU or leaky ReLU. Sometimes they have or in these cases, you have modification that it's, for example, not cut off at 0, but it has a more smooth cutting off in the negative area, that you allow also some small negative values. Very important is data preprocessing, because the whole network, you can have a perfect network and the whole network optimizes in a really good way, but when you change for example, the normalization of the data, the whole network might be diverging instead of converging. What is a good way, or what works for many different data types, is some kind of normalization, that you have the data and put it into a range between 0 and 1, or -0 and +1. This is also easy to work with, because you do not have very large values, which will lead, for example, to exploding gradients, or you do not have very small values, which leads to vanishing gradients. So you start with a good range, good values, and help the network to converge in a good way. What is done in remote sensing area very often is a so-called set normalization, or whitening. What you do here is you first shift all the data to 0 mean, and then you normalize by the standard deviation. Be careful if this makes sense for your data. For example, when you have a hyperspectral signature and you have red values, or values in the red channel and values in the near infrared channel, and you divide them by the standard deviation, the relation between red and near infrared will get lost. So you cannot tell anymore something about the health status of the plant. Overall, you need to think about what you want to normalize. If you want to normalize the bands, or if you want normalize over the data, that you, for example, just subtract the maximum value of the whole data set. There are different possibilities. Normally it works quite well when you just have the data in a good range in the early beginning, as I said, between -1 and +1 or 0 and +1. Related to this is the weight initialization. It's the same here. When you start at a point in the loss landscape which is not so good for convergent behavior, you will have a hard life to make it converge in a good way. What the first thing which comes to your mind might be just a random weight initialization. That means you have, for example, you initialize the weights with a normal distribution. All weights are normally distributed with 0 mean and a specific standard deviation. When you choose a small standard deviation, this can lead to problems when you have a larger network. And here exactly these vanishing gradients problem appear. If you, for example, imagine you start with small weights, smaller than 1, and then you multiply them again with values smaller than 1 again, and again, and again, and again. So it will get smaller and smaller and smaller. And in deep layers, you will end up with gradients which are close to 0, and so nothing happens anymore. So the later, deeper layers will not help you for your task. Another possibility is when you initialize with all the same value, for example with 0. This leads to the problem that, for example, nearly all neurons perform equally with equal gradients. And when you think of this loss landscape, it's very unique, and at each point it's not that you have in various direction a similar behavior. What you want to do is a gradient update in each direction in a specific way, but this is hard to accomplish when you start with the same value. So this is also not a good choice. A better choice is, for example, the so-called Xavier or Clairaut initialization. Here, it also depends on the number or the value the weights are initialized with. Also depends on the number of input neurons and output neurons. This prevents the whole network from vanishing and exploding gradients, and so the activations are in a similar range throughout all layers. And if you have similar valued activation, that also means you have similar valued gradients, and this is exactly what you want to have. You do not want to have totally different gradient updates in not so deep layers and deep layers. So another very smart way for weight initialization is to use pre-trained networks. What does it mean? There are some architectures, some network structures which are quite common and which turn out to be very useful for specific tasks. What you can do is you just take an existing architecture, and you do not take only the architecture, but you also take the weights, and you use the weights and use these for your task. What you can here see on the slide is a very easy scheme of such a network. So you have an input, and then you have the feature learning process. That means here are all the hidden layers where you learn a new representation of your data. Then you have the specific task solver. That means either you want to use it for regression or for classification. So you have your linear layer or your softmax or sigmoid layer, and then you have an output. And now you have different possibilities to use existing weights from other tasks. So imagine someone trained the whole network on another task. So for example, the other person trained the network on to distinguish between two classes. One is, for example, a forest, and the other is agriculture field. And now you want to use the weights because this task might be quite similar to your task where you want to distinguish between bare ground and plants. This is done very often, and here you have possibilities what you want to take and use and what you want to retrain or fine-tune. So green indicates that this is retrained, and white indicates this part is fixed. And so the first possibility is that you have an input and the output, and you just retrain the whole network. This is very, very good to adapt the network in a specifically to your task, but it would take very long sometimes, and especially when you have a lot of data points and you need all the data points to retrain your network from your initialized weights, which came, for example, from a chloro initialization. Another possibility is that you only retrain a few layers, so not all layers. And if you fix the first layers, this is a really good idea, because in the first layers normally features are learned which can be used for very different tasks. So the deeper the network is, the deeper layers learn more complex and more task-specific features. So when you want to retrain only a part of the network, it's a good choice to retrain the last layers and not the first layers. And another possibility is that, for example, you fix the whole hidden layer structure, so you use the weights which are used there, and you only retrain the very last layer where you solve the task, for example, the classification or the regression layer. These are different possibilities. Also, it's not black and white. That means it's not that you fix that you only can fix it and retrain it. You can also retrain at a specific level. For example, some layers can be retrained from the early beginning, so totally new, or some can just be a little bit fine-tuned. That means you keep the ways, you take them over, but you adapt them in the last iterations, for example, when you do this whole optimization process. So this is very task-specific and depends on, for example, how many labeled samples you have and how similar your task is to the task the network was trained on. So what you can see here is some suggestion depending on what you should retrain, depending on how similar the data is and how many labeled samples you have. With data similarity, this can be tricky because it's hard to say how similar a task is to another task. But if you, for example, have area images or satellite images, of course, it's quite similar to other satellite images. But if you have close range camera images, it might be not that related to satellite images as if you have only two tasks with satellite images. And as I said, there's no black and white and retraining and not retraining, and also the amount of layers you want to retrain can be selected and chosen by you. There are some quite famous, quite commonly used pre-trained networks out there. For example, the mask RCNN. This is a network which you can use for instance segmentation and object detection. ResNet, for example, can be used for classification. Also MobileNet. MobileNet is a very efficient network. Because sometimes you do not have for some applications you cannot use huge networks like in robotics. there you need to be very efficient and have small architectures. And also there's always a combination. So the combination of the network and the data set it was trained on. And popular data sets are, for example, ImageNet, which has 14 million images and 20,000 categories. So this is used for classification and detection tasks. Also MS COCO. Here you have 1.5 million objects and 80 categories. So there are, have a look at the links and you will see there are many pre-trained network architectures, and I would say that this is the common way to go if you do not just want to experiment a little bit. A very crucial hyperparameter you need to choose to have a good training and an efficient training is the learning rate. So I would say this is even the most important hyperparameter. So before you want to tune other hyperparameters, always first try to optimize the learning rate and choose a good learning rate. There's no optimal learning rate, but there's a bad choice and a good choice. And let's first have a look at the update equation. So what you want, what you have there is you have the gradients, which is the nabla E. This is the gradient vector, and then you have your current parameter vector, which is W, and your updated parameter vector W up. And the learning rate is nu, and nu is a scaling factor to the gradient. So it's because you only want to move locally in the loss landscape, you apply this learning rate, so you can move locally, and then you can evaluate the gradient again, and then you move that you can reach the optimum in a good way. What can happen is that you choose the learning rate too high or too low. If you choose it too high, you can see a behavior in the loss curve, like the blue curve. So what you can see here is the number of epochs and how this loss function value develops over time for the training data. What happens here is when you apply too much of the gradient, you're not moving in a small local area in the loss landscape, but you apply the gradient in such a large value of the gradients that you just overshoot, and you end up with a higher loss function value than before. So it's you need to be careful how fast you proceed with your optimization. The other extreme is when the learning rate is too slow, too small. That means the movement of the gradient, or how you proceed to reach an optimum, is just too slow. You can see it when you have such a nearly flat loss curve. And so even after many epochs, you will end up with an only small decrease in the loss function value. So these two behaviors are quite good to detect. So you can react in a way that you decrease or increase the learning rate. What is not so good to detect is if your learning rate is just a bit too high. What happens then? It can be best seen with the following illustration. For example, if you have the loss landscape around a local optimum or even a global optimum, if your learning rate is too high, it happens that you just jump from one side of the loss landscape to the other side. So because it's too large, you just jump to the other side and back, and so you are never able to reach or to go down to a smaller value of the loss function. So what you can do is you just decrease the learning rate, but you can see Actually, if it's just a bit too high, this curve looks similar to when you have a good choice, because it's converging in a good way. It's not diverging, or it does not show this very flat behavior. So it's always a good idea to play around with the learning rate a bit, or to have some learning rate scheduled. I will talk about it on the next slides a little bit more. And yeah, another thing which can be an indicator that you should decrease your learning rate is when the loss curve jumps around. You can see it when you have a look at the epochs, and when at some point it's not decreasing anymore or increasing, it's just jumping around like this. And this sometimes you can see it, it's very distinct, you can see it immediately, and sometimes it's a little bit hidden, because we talked about the stochastic gradient descent and the choice of the batch size, so you also have a little bit this jumping around. But if it's very large, it's an indicator that your learning rate might be too big. So another interesting thing you can observe when you have a look at the learning rate is not only look at the loss function value, but also have a look at the accuracy. And sometimes it can happen that they behave in a different way. What you normally expect is that you have somehow some kind of mirrored behavior. So if the accuracy go up, you expect that the loss curve goes down in a similar way. This is mostly the case, but sometimes it's not. This can happen, for example, if you use a softmax function or a sigmoid function as an output in the output layer. That means your output is squashed between 0 and 1. That means you have somehow probability as an output. When you have a very hard to solve classification task, it can, with two classes, it can happen that a lot of data samples are classified near 0.5. That means the network cannot really distinguish if it's class 1 or class 2. But so what you see is that the train loss, if it's near the 0.5, the train loss will not change that much. But if you look at the accuracy, if it switches from a little bit larger than 0.5 to a little bit smaller than 0.5, the whole class changes. And when you compute the accuracy, this can change a lot. So if it happens such a switch in the class assignment for many samples, the accuracy can change a lot, but the training loss will not. So in this case, you observe a different behavior of the accuracy and the loss. And this is exactly a sign that the classifier is not that sure about the assignment. But when you have a look at the score and the probabilities as an output, you will also observe this. So what works mostly in practice? Start with a reasonable learning rate. A reasonable learning rate is around 0.1 or 0.01. In case you normalize your data in a range between 0 and 1 or -1 and 1, or around this. Of course, if your data is normalized in a different way, you also need to choose a different learning rate, because then also your gradients will change in scale. So start with a reasonable learning rate which suits to the normalization you apply to your data, and also a small regularization. I haven't talked about the regularization specifically, but if you want to apply it and to regularize and stabilize the whole optimization process in a little bit more targeted way, start with a small regularization and then try to increase it. A very good suggestion when you start and you have no idea about the behavior of your data, try first to take a small subset of the data and try to overfit the network. Because if you are not able to overfit your network with a small amount of data, it will not work with a lot of data. It should be easy to overfit a network when you do not have a lot of data. What I mean with a lot of data is when you see the number of parameters you have in your network and the number of labeled samples. If the number of labeled samples is much lower than the number of parameters, you should be able to overfit the network. So if this is not possible and if something just does not work, you should change the architecture. It might be not complex enough, or the loss is not suitable. Sometimes the standard losses are not the best choice for your task. It always depends on the task. And maybe also the hyperparameters are inadequate. So what I told you, crucial hyperparameters are the learning rate, or maybe your regularization is too high. This can also be the case. Always monitor the training and the validation loss. As I told you already, you can learn a lot from how the optimization procedure is going, or what is going on in your network and where you are in the loss landscape based on your training loss. But it's also necessary to have a look at the validation loss and that you do not observe this elbow effect and that your validation loss and the training loss differ too much. And then adapt the hyperparameters. So if you are able to try to overfit with a small sample size and you apply the network to a larger set, or even the whole training data set you have, you need to tune hyperparameters. And this can be a very long process. That's totally normal. That's okay. But once you have it and you have a good hyperparameter set, generally the neural network is a quite powerful task solver. So it's worth to do it. And speaking of hyperparameter search, so far I told you always only choose a hyperparameter, choose in a good way, in a reasonable way, but because there are many hyperparameters, this can be very inefficient and also subjective. And sometimes you have no idea about how you can test all these hyperparameters in combination. So there are better ways, there are more efficient ways, and the better choice to do it is via cross-validation. So what you do here is you have your training set and your test set, and as I told you, never touch the test set, treat it as not existent. And then in the last lecture I told you, you should split away a small validation set and treat it as an independent set and use it for the hyperparameter tuning. Even better way is when you do it via cross-validation. That means you split the training set in equal sizes, and then you use always n-1 parts with n the number of sets you divided your set in, and n-1 are used for training and the last one is used for validation. And so you very safe in that you always have a validation set, and also you get the whole variety of the validation set and the training set. So you have different results with it, and for all these training and validation sets you can use for different hyperparameter settings, and then you average all these results in the end. This is more robust than if you only decide on one validation set, but of course it can be yeah, it can be very inefficient if you do it with a lot of these sets. So if your data set size is very large and you do not have enough time and not enough computing power, just use at least one validation set. So this is you should always use a validation set. And if you can, do this cross-validation thing, that you also change the training set, the actual training set and the validation set. And a nice procedure to search for hyperparameters, you first think of which hyperparameters you need to tune, and then you set a range for a search. So when you know how you normalize your data and you have some idea about a suitable range for your hyperparameter, for example the learning rate, you decide on this range. And then first of all you do a coarse search to get a fast impression. So it's you just, for example, if you have a specific range, it's not that you test hundreds of these hyperparameter settings in between. You just search with a few of them to get a first impression. And it means only a few values. And also for you do not need to make a whole optimization process for this exact hyperparameter setting, but you can decide on a few epochs. So you will very fast get a good impression on which hyperparameter setting works and which setting does not. And after you got an impression of the hyperparameter settings, you do a fine search. That means you restrict the search space, because now you know in which area are good parameter values, and then you can make a fine-grained search and search for a very good hyperparameter setting. Okay, so here I made an illustration when you, for example, search for two hyperparameters. One hyperparameter could be the learning rate, and the other hyperparameter could be the number of layers you use for architecture. It's a good way, a good idea to search in log space instead of the uniform search space. For example, when you have when you think about the learning rate and updating the gradients are updated by multiplying. And to get a more uniform multiplying effect and to get an impression which hyperparameters work and which not, you can do it in a log space, and you get a better impression which range of hyperparameters work, and that means which learning rates are suitable to solve this task. When you do a coarse search, here you can see low values are indicated in dark colors and high values are indicated in with bright colors. And when you have all these combinations of parameter 1 and parameter 2, you get this result of this grid search, and you have one area which shows low values. And this is actually what mostly happens. So it's not that you have some kind of noisy effect. So it's not that in one area hyperparameters work, in another area. It's mostly restricted to one area. So it's very, you mostly get a homogeneous result. So this darker area indicates that you should have a closer look to it. And then you can do a fine search, and again you do this parameter combinations of parameter 1 and parameter 2, and you will see that there's again one area which is quite dark, and then you choose exactly this combination of these two parameters, and to use for the optimization process, or the final stage of the optimization process. You need to be careful, and it's good to illustrate this. So have a look at the results and the parameter combinations, because it can happen that when you go from the coarse range, the coarse search to the fine-grained search, that you chose the area for the fine search too small. You will see this when you then the best parameter combination is at the border. So here's a good idea to extend the search space and explore exactly this area where settings of hyperparameters will lead to good results. Another result related to this, what I said, mostly you get a homogeneous result. It's very suspicious when you have a very good or low loss for a parameter combination, but if you change the hyperparameters a little bit, you get high loss function values. This is suspicious. This can happen, for example, when you made maybe not the best choice for your training data set or your validation set. And especially this is the case when you do not have a lot of training data, and this is unfortunately very often the case for remote sensing. So have a look, illustrate it or plot it, and then see if it's either if either your search space is not large enough or if you have a suspicious result. Another thing, another suggestion is not to do this hyperparameter search in via grid search, but instead with a random search. What mostly happens is that you have a very important, highly influential parameter, for example, the learning rate, and another one which is not that influential on the result. For example, normally it's not a big issue, not a big difference if you have 15 layers or 16 layers. So, but what can you do if you want to get a better impression what is a good hyperparameter setting is you set the range, but then you sample randomly for the hyperparameter settings, and then you determine the loss function value for it. So on the left side, you see it when you do it in a very structured way. That means in a grid. And on the right side, you see it when you do it randomly. So this yellow curve, or this yellow area, and the assigned curve is the loss function values of the unimportant parameter, and the green area, the green curve, is the loss function value distribution of the important hyperparameter. And what you can see it, if you do it in a very structured way, in a grid, you get only three values of it. But if you do it in random search, you you cover this distribution much better, and you get a much better impression which parameter, hyperparameter, will be good to solve your tasks in a good way. So it's a good choice to do it this way. The important thing is that you get the correct range, and that you search in a good range. I want to talk a little bit more about gradients and the loss landscape. And remember, the stochastic gradient descent was that you compute the gradient, and then you apply the learning rate to the gradient, and then you use this as an update to your current parameter setting. So far, I told you only that the loss landscape is a very complex, non-convex landscape. But what I didn't tell you so far, what you can, which structures you actually have in this loss landscape. And one is these valleys which look like a taco shell. And when you are somewhere in this taco shell valley, you will observe that if you compute the gradient and you do this over a few iterations or a few epochs, you will observe that the loss change quickly in one direction and slowly in another direction. So what happens is, imagine you're of one side of the taco shell, and you have a high gradient in one direction. You will likely overshoot in this direction, and in the other direction is the gradient is very small. So you would so you move not so much in this direction, but you apply the same learning rate. It's not that you apply a different learning rate for different dimension. So what happens is that you have the zigzagging behavior. So you're moving very slow in one direction, but you're overshooting all the time in the other direction. And then you do the zigzagging in this taco shell. And so in this way, the stochastic gradient descent will progress too slow, and you need to do something about it. And there are some modification of the stochastic gradient descent I will show you in the next slides. So what you can observe in this loss landscape are a lot of local minima and also saddle points. And so here I illustrated both for you. And what happens if you use if you compute the gradient, and you will likely get stuck exactly in this local minima, because you will not go further. And also the same with the saddle point, because if you are exactly on the saddle point, your gradient will be 0, and so no update will be applied, and so you are stuck. So in both cases you will get stuck because you have 0 gradients. Also in the local minima, you cannot move right and left. It's just it's just 0. And this is a problem because saddle points are quite common in high dimension. Not that much local minima, but saddle points are quite common, because a local minima is defined that you have it goes up in all directions, in all dimensions, but it's much more likely that you have that it goes down in a few directions and up in a few other directions. So local minima are not actually quite common, but saddle points are. But at saddle points, again, same problem, 0 gradient, and you would just be there, and your network will not, the weights will not update anymore. And it's also, even if you manage to not get stuck on the saddle points, if you are very close to a saddle point, the progress will be very slow. Therefore, you need more sophisticated method. And when you play around with some software tools for neural networks, or if you program your own neural network, you will realize that you always can, or that you can choose between different optimization techniques. And stochastic gradient descent might be one, but there are also other ones. And they have some tricks which prevents you from getting stuck. And let's have a look at the standard gradient descent again. So what you do have here is learning rate alpha. The gradient is indicated with this nabla E. Parameters are W, and W up are the updated gradients. When you use, so there's a simple strategy that adds momentum to the gradient, and momentum can be seen as some kind of velocity. So even imagine you're making progress in your loss landscape, and at some point you're getting stuck. If you have a momentum, you have some velocity. So even if you would get stuck there, you still have this velocity and this momentum, which brings you exactly over the saddle point or out of this local minimum. And the velocity is nothing else than the running mean of the gradients. And here's another parameter which is used, which is actually not so bad, because this rho is the friction, but this friction is generally just set to 0.9 or 0.99, so you will be quite okay in choosing this kind of value. And this is good because you will not get stuck. And illustrated here is exactly what happens when you add the momentum. So it will bring you out of the local minimum again and over the saddle point. And so the zigzagging is also cancelled out. This is a nice property. because it's when you go, because this is a running mean of the gradients from the last few iterations, and the zigzagging happens that you adapt too much to the new situation, and because you have a running mean and you apply the running mean, the zigzagging is cancelled out in a and you get a more smooth way to an optimum. One picture you can have in mind when dealing with momentum is exactly this illustration, illustrating some vectors about the velocity and the in the gradient, and the actual step you take. So what you do is on the left side is the basic momentum. You have the gradient which points in one direction, and you have the velocity, which is the smooth moving average over the gradients from the last steps. And in the end, you have the actual step you take. And this is exactly when you think about the zigzagging. So it's not that the gradient moves from here to here and back and forth. So it's more like more smooth in the end. There are also different possibilities, different momentum. I just want to mention it, that there's not only one momentum, but more. So the Nesterov momentum, for example, is that you first take the velocity, so you apply the computed velocity vector, and then where you end up, there you evaluate the gradient, and then you apply the gradient. And so the actual step which you take is different than in the case where you evaluate the velocity and the gradient at the same point in the loss landscape. So good initialization for the velocity is just 0, because at some point you need to start. So there's another common strategy for optimization, which is called AdaGrad. AdaGrad is short for adaptive gradient algorithm. So instead of using the velocity, here you take a running sum of the squared gradients. So not only that you take the squared gradients of the last few iterations, no, you start from the very first iteration, and then you sum them up over all the time. And all these gradients are stored in a matrix G. And what you do is to the actual update you apply to parameters in the end is you have an element-wise scaling of the gradient by the sum of all previous squared gradients in each dimension. The main benefits are that if you have a large value or a large gradient, you divide by a large number, because then all the gradients before are likely also very large. And if you have a small gradient, the running sum will be also small. So it speeds up, in case you have small gradients, it speeds up the process. If you have large gradients, it stops it a little bit. So in the end, you have a very smooth optimization over the whole time. The main weakness is the accumulation of the squared gradients over time. That means since every added term is positive, that the value of the matrix grows and grows over time, and at some point, when you look at the equation, because you divide by this matrix or the values in the matrix, it gets so small at some point you will not get an update anymore. So the more epochs and iterations you have, the smaller the overall update step gets, and this is the disadvantage about it. There are even more improved optimizers. So what I showed you here is some kind of development. So every time someone came up with a new optimizer, it was quite good, mostly better than the previous one. And then you realize some disadvantages, and then you develop it further. And further improved optimizers are, for example, the root mean squared propagation error, RMS prop, and ADAM. And Adam is a really good optimizer. So in case you do not know and you do not want to take care of which gradient and which way you can choose, normally Adam is a good choice. So Adam optimizer is a sort of MS prop with a momentum, and MS prop is equal to AdaGrad, but force decay in the sum of the squared gradients. So it's not that you apply them all the time in the same way, that it grows larger and larger, but you have a decay in which you sum the gradients over time. And so Adam, mostly a good choice. And another thing in combination which needs to be mentioned is that you can also have a learning rate decay. So when you apply the gradient and the learning rate, it's not that you choose the same learning rate, or you don't need to choose the learning rate the same learning rate over the whole optimization procedure. You can also use a decay there, because during the optimization procedure, the loss landscape would change, and also how good you already, or how close you already are to your optimum, and you do not want to miss it. So what you can do is, or what typical strategies are a step decay. So for example, you start with very high learning rates, because in the early beginning you are somewhere in the loss landscape and you want to make progress. It's why you can choose a high learning rate in the beginning and apply the gradients, large gradients, and to make progress. And at some point when you close to a good optimum, you just slow down and search to settle somewhere. And this you can do with the step decay. There's also an exponential way. It's not that you reduce it after a while by a specific amount, but you do it in a smooth exponential way. Or also you can do it with a 1 divided by t decay. This is another possibility to have it a little bit more smooth. So when you look at papers sometimes, you will, and they plot the learning curves, you mostly see such effects that you have a learning curve and then it converges a bit, and then you have such a step, and you make some more progress, it converges again, and then you have such a step again. And this is a sign for an applied decay. So you cannot reach a better optimum with a large learning rate. So what you do is you reduce it, that you can settle down more in this optimum. This is exactly this effect, which is what I showed you a few slides before, when you jump around from one side to the other side in the loss landscape. And another really cool technique which came up in the last few years is the so-called superconvergent. And that was quite interesting because it contradicts exactly what I told you in the last slides, that you do not start with a high learning rate and end up with a small one. You start with a small one, and then you you increase the learning rate. So what you do first here is you make some dry run, and you start from a very slow learning rate, and then over the epochs you increase the learning rate. And why are you doing this? You want to know which is the maximum suitable learning rate which can be applied in this loss landscape. So the minimum value is quite easy to see. I mean, at some point you do not make any progress anymore, but the maximum learning rate is mostly hard to see, because this depends exactly on the structure of the loss landscape. And now what you do with it is the following. You start with a very small learning rate, because when you start in a loss landscape, the gradients in the early beginning need a little bit time to orientate themselves and to just settle a bit, to see what is a good direction to go. So when you immediately start with a high learning rate, it's very likely that you just run around and go in a wrong direction. But if you start with a small learning rate, you can first settle a bit, find a good direction, and then you increase the learning rate and to reach very fast, in a very fast and efficient way, some optimum. And then this, what I told before, is applied. So at one point, it's you will not reach anything better, any better result with a high learning rate. So you decrease it again and settle down in the optimum. So first of all, orientation. Then you speed up the process. You find a good direction, and to reach the optimum. Do it in a fast way, and then you settle down. And this turned out to be a really good way. It's called one cycle learning schedule. It's implemented in many software packages, so you can use it. So what works mostly in practice is you don't need to use a decay. You just monitor the loss and see if it might help you in fast and efficiently optimize for your task. And then you decide on a learning rate schedule. So you can use just this decay or this one cycle optimization, or you just leave it. Maybe you decide you don't need it for your procedure. And also important to mention is, if you use ADA, I told you this is already a combination of this momentum and some decay in there. So it can be enough to use ADA optimizer, such that you do not need any further schedule for a decay in of the learning rate. You need to try it out, and you need to see if what works for your task. But this is what you can do and what you can try. Another important thing I need to talk about, independent of the gradients, is data augmentation. Data augmentation is also important to ensure a stable and robust optimization process. What you do here is, when you do not have a lot of data, and if your variety of your data is not that big, or maybe not representative of the whole data set, you can do data augmentation. Data augmentation is you artificially increase the amount of training data. You do this by transforming your labeled samples by some transformations. For example, when you have images, you can flip them, you can rotate them, you can add noise, do sample crops, and also all combinations of them. So it's quite easy to increase the amount of labeled data a lot with simple strategies. And because you have a lot of data, then it's more robust, and the whole process, the optimization process, is stabilized. And you can see here some images where flipping and rotating is applied, and you can see nothing changes about the input. But you can increase the number of samples in a nice way. Yeah. It's just like making more observation by changing the settings or by changing the environment, and you can just do it artificially. Be careful, this works quite well with just random images, like yeah, when you have some, if you take images with your camera, but if you have scientific data, for example, like hyperspectral data, it's not not every augmentation makes sense. For example, if you have an hyperspectral image, of course you can rotate it and flip it. Totally okay, but if you look into the spectrum, here you cannot do some augmentation because you cannot just you cannot flip it, and it would not make any sense, and it's not representative anymore to reflect the spectral characteristic of a material. So be careful what you do augment and where you apply these augmentations. So as a last thing, I want to talk a bit more about neural network architectures, because there are different architectures. I showed you so far a standard, fully connected neural network, a very simple one. But depending on your task and what you want to do, there are different architectures. And with architecture, I mean the way in which neurons are connected together. So here you can see yeah, a quite famous illustration of different network architectures. It is called the neural network zoo. And you can, on the left side, you can see a lot of different kind of neurons, which are then connected in different ways, resulting in different architectures. You can have a look, a more detailed look when you go to the website. It's quite interesting. Which architectures exist, and of course there are a lot of more modifications which you can find. So I want to focus on one specific property an architecture can achieve, and this is that you compress the data. You can easily compress the data by reducing the number of neurons the deeper the layer is. So you start with a lot of neurons. Here you can see the red ones is your observation data, your input data, and then you reduce the number of neurons, and in the next hidden layer you decrease the number of neurons even more. And if you compare the input dimension with the last layer, you can see that this has a lower dimensional representation. So you come from in this case 6 neurons to 2 neurons, so you have a 6-dimensional space, and then you end up with a 2-dimensional space. And this is something which many neural network architectures use, and you can use it for a lot of tasks. And when you have it symmetric, you speak about the hourglass encoder decoder, because it has the shape of an hourglass. The hourglass encoder decoder is not only that you compress the data, but then you go back to the original size of your input, your input dimension. And so you have, when you compress the data, it's called encoder, because you encode the data to a new data representation. The exact middle layer is called the latent vector, the bottleneck, because this is exactly where you have the lowest the dimension of the representation. And then you go back, and this is the decoder. So first you encoded the data, and then you decode it again. And mostly you end up with the same dimension of the output as the input. And one very nice example where this bottleneck hourglass encoder decoder is used are autoencoders. Autoencoders are an architecture which are used when you want to reconstruct your input data. So what actually, it sounds very simple. It is, but it's very powerful. So what you have is you have your input, it's also your output. And what is happening in between is you feed your input data to the autoencoder. then you encode this to a new representation. In the bottleneck layer, you have a very compact representation of your input data, and then you try to decode it in a way that you can reconstruct exactly the input data. It's not an identity mapping exactly because of the bottleneck layer. If you would not reduce the dimension, and if you would not have this hourglass structure, you will end up with an identity mapping. But why is it good? When you do this encoding, you lose all these unimportant features which are useful, are not useful for any task. For example, you can do denoising, because noise is not an important structure in an image, or you can use it for data compression in general, or also for anomaly detection. For example, you can have a lot of images of healthy plants. You can learn a representation of how healthy plants look like with an autoencoder, and you capture exactly the important structures of this kind of data. And if you apply this learned autoencoder to new data, and for example you have diseases in these plants, you can detect them because the autoencoder is not able to reconstruct images with a diseased plant, because it never learned it. I never learned these structures of a diseased plant. So in this way, it can also use for anomaly detection. So autoencoder, very nice tool, works in an unsupervised way. So you can learn an autoencoder without using labeled data, and this is also quite nice and useful for many tasks. One modification you can do is to make it a little bit more robust, because in many cases autoencoders are too good. They're very fast, very good in reconstructing anything you want to do, and the middle layer need to reduce a lot to prevent this, and to help the autoencoder a little bit more to find important structures in the data is when you use denoising autoencoders. What you do here is you have the original input data, and then you add noise to your input data, and then you apply this encoder and decoder, and the output is not now not the input, but it's the input without the noise. So you have a noisy input and not noisy output, and this stabilizes it a little bit more, generally gives better results than the standard autoencoder, and you help the network to learn the important structures a bit more. As an example, I told you in the bottleneck layer you have this latent space, and this latent space is much more lower dimensional than the input space. So what you can see here is a part of a grapevine, and you have an original image in the upper left corner, and when you you can see here different sizes of the bottleneck layer. So the size of the bottleneck layer is determined by the number of neurons, and you can see if you if you go from left to right and in the top row and then in the bottom row, in this here is the size of the bottleneck layer is increased, so you use more neurons, and when you use more neurons, your autoencoder can reconstruct even more. So in the beginning, if your latent space is not so big, you can see the color is not reconstructed that well, but if you increase the number of neurons in the latent space, you can reconstruct more and more details. You can see it also when you have a look at the rope, so you get more detailed reconstruction, more fine-grained reconstruction, or when you increase the latent space. But again, there's not a rule of thumb how big your bottleneck layer should be, and how many neurons you should use there. you need to try, and mostly depends on the of the complexity and the structure existent in your input data. So to sum up, so what I told you today was a little bit more, some advices, some suggestion, and how you can train your network and what possibilities you have, and if you want to tune your hyperparameters, what kind of hyperparameters you can tune, and specific ways you can do it, and also how you can speed up the optimization process. In the end, I showed you that the neural network zoo is huge, and very likely, if you have a task, you will find a suitable network structure for this task. But you need to think about the training procedure, and it requires to think about it and a thoughtful choice of all the components. And as take-home message, I want to tell you that a feeling for good choices helps a lot, and you need to try it out. And the feeling, to get a feeling for it, you need experience. That means you need to work with neural networks, and after a while, you will get a good feeling in how to choose the hyperparameters, and also which architecture will be suitable for your given task. And yeah, it's always a new challenge when you change the kind of data you're working with. Yeah, this is what I wanted to tell you in this lecture. The next lecture will be about convolutional neural networks, and with this I say thank you for your attention, and yeah, hopefully see you in the next lecture.